Hello, my name is Maria Ishira binti Mazlan and my register number is 2250013. Today I would like to present about introduction. Tower cranes are essential assets in modern high-rise construction engineered to lift and position payloads of several tons at immense heights. In the realm of engineering mechanics, a tower crane serves as a premier real-world application of statics, the study of bodies in a state of constant equilibrium. While a crane is a complex system of interconnected rigid bodies, the critical point where the lifting cables meet the payload or where the support guy wires converge at the top tower apex can be precisely modeled using the equilibrium of a particle in 3 dimensions. The systems are subjected not only to vertical gravitational loads but also to lateral wind forces and angular cable tensions. Analyzing them in a 3D coordinate system is vital to preventing catastrophic structural failure. So the second one is project overview. So for the project overview is to guarantee structural safety and prevent the crane from buckling or twisting under multi-directional loading. This engineering analysis fulfills the following specific objectives: 3D particle equilibrium formulation to establish a complete three-dimensional Cartesian vector system at the primary cable nodes, satisfying the fundamental equations of particle equilibrium, multi-directional cable tension calculation, asymmetric load stability assessment, material and safety margin verification. That's all from me. Thank you.
I will talk about literature review. Tower cranes are essential equipment in modern construction projects, especially for high-rise building and large infrastructure development. They are used to lift and transport heavy material efficiently across construction sites. Their stability and safety relay the principle of static equilibrium, where all force and moment acting on the structural mass remain balanced. Factors such as lift load, counterweight, wind force, or foundation support significantly affect crane performance. Therefore, proper static analysis is important to evaluate load distribution, ensure structural stability, and maintain safe and efficient crane operation while reducing the risk and accident and structural failure.
Moving on to the problem definition, where we analyze the system of the crane apex particle equilibrium model. The core problem of our analysis is to determine the unknown tension forces in the supporting cables when the crane is holding a specific load. In a real-life engineering scenario, failing to accurately calculate these forces can lead to structural failure or cable snapping. To solve this, we isolated the apex, which is the very top point where the cables meet, and treated it as a single particle in a three-dimensional space. By identifying all the external forces, such as the system weight and the wind forces acting on the crane, we mapped out exactly how the forces are distributed before moving on to the calculation. Moving on to mathematical modeling. In order to convert this physical system into mathematical equations, we used vector mechanics in three-dimensional space. Firstly, we represented our forces in terms of Cartesian vectors, where the vector representing the system weight was along the negative z-axis and the external forces were along the y-axis. Secondly, we obtained the position vector for each cable using their coordinates, from which we obtained the unit vectors. We multiplied these unit vectors with the magnitude of the tension which gave us the tension vectors. Thirdly, we applied the Kirchhoff static law of equilibrium that states that the sum of all forces must equal zero. This provided us with a system of three linear equations in order to determine the tension of the cables.
Moving on to the results section, the three-dimensional particle equilibrium analysis was applied to determine the forces acting on the apex node of the Liebherr ECH280 tower crane. In this study, the apex node was analyzed under the combined effects of payload weight and crosswind loading. Since the exact attachment coordinates were not provided in the case study, reasonable geometric assumptions consistent with the actual crane configuration were adopted. Using the equilibrium equations in the x, y, and z directions, the tension forces in the support cables were determined. The front tie cable tension was calculated to be 18.71 kilonewtons, while the rear tie cable tension was found to be 24.65 kilonewtons. The results indicate that the rear tie cable carried a greater load compared to the front tie cable. This difference occurred because of the geometric arrangement of the support system and the distribution of forces acting on the apex node. Finally, verification of the equilibrium equations showed that the system remained in static equilibrium under the specified loading conditions. These findings demonstrate how three-dimensional statics can be applied to analyze and evaluate the behavior of real engineering structure. Moving on to the discussion section, the analysis showed that the rear tie cable experienced a higher tensile force than the front tie cable due to the geometric arrangement of the support system. The inclusion of crosswind loading also highlighted the importance of considering three-dimensional forces when analyzing tower crane, as real construction environments involve both vertical and lateral loads. Several simplifying assumptions were made during analysis, such as treating the apex node as a particle and neglecting dynamic effects like vibrations and wind gusts. Despite these assumptions, the study successfully demonstrated how the principles of three-dimensional statics can be used to assess stability and safety of tower crane system in practical engineering applications.
In conclusion, the 3D practical equilibrium method was successfully applied to analyze the apex node of the Liebherr ECH280 tower crane under payload and crosswind loading. The results show that the rear tie cable carry a higher tensile force, 24.65 kilonewton, than a front tie cable, 18.71 kilonewton, due to the crane geometry. Equilibrium verification confirmed that the system remained stable under the assumed loading condition. This study highlights the importance of consideration both vertical and lateral load in tower crane analysis and demonstrate the role of engineering study in ensuring safe and reliable crane operation. Thank you.